Hello and welcome to another Cloud with Chris livestream. You are with me, Chris Reddington. Here we talk all things cloud, and thank you folks for joining. Hope you are keeping well. We've got a really interesting topic for this evening's stream. We are going to be talking about Azure Quantum. We're going to be talking about Microsoft Q Sharp, and I'll be honest, I'm completely out of my comfort zone. I am completely not in my territory whatsoever with this one, but I'm looking forward to learning a lot and hopefully getting a bit more understanding. I'd say it's not rocket science, but there's surely some kind of science involved. But by no means it will be a lot of fun talking about this evening. So let's bring in the guest for this evening. He's backstage. Here he is, Mr. Johnny Hooybergs. I think I got that right, hopefully.
Perfect. Thanks, Chris.
Thanks, Johnny. No, thank you for being here. Glad to have you here. I think, like I mentioned there, really interesting topic. I guess quite niche and specialized, I would say.
Yeah, it is.
So maybe some background first around who you are and how you got into this.
Yeah, indeed, my name is Johnny Hooybergs. I'm from Belgium. So I'm actually a software developer and consultant for a company called Involved in Belgium. And I'm just doing regular software development stuff, basically in Microsoft-related technologies like .NET and Microsoft Azure. And yeah, of course, I have some free time, not a lot, but I have some free time. And sometimes I try to do something new and exciting. And that's how I kind of rolled into quantum. So just to be clear, I'm not doing it professionally. It's just basically a hobby that got quite out of hand. I think it was about 2017, maybe 2018, where I was visiting a software developers conference in Belgium called Techorama. You maybe heard of Techorama?
Very familiar, yes.
Yeah, so I was there as just a regular guy going to a conference, and I saw a talk from one of my favorite speakers, which is Bart de Smet. He is Flemish. He has a Flemish origin, but he works for Microsoft. And he was talking about this new spectacular language called Q Sharp. And I was like, a new language, quantum computing? I have no idea what that means, but I like Bart, so I will join his session. And after 1 hour of typical Bart de Smet stuff, I got a slight headache, almost a bleeding nose, but not quite yet. But I didn't really understand most of this session. I knew what it was about, but when Bart got into the details, I kind of basically lost him. So that's when I decided to look into that topic myself a little bit, because when I see something that I don't understand, I really want to understand it. So after Techorama, during the summer months, I looked into it. I tried to teach myself. I tried to learn more about it. And then from one thing came another. My boss for the company I work, he found out that I was reading into this stuff, and then some kind of college in Belgium, they wanted to have like a special talk, like about a niche new technology. And my boss basically told me, why don't you go talk about quantum? So I did a talk on quantum computing for this college, for this school. I really liked it. I got very good feedback. Then I tried doing like conference talks about quantum. Many conferences accepted my proposals, and I was doing that. Got really good feedback from that. And yeah, again, one thing came another. I needed to really dig even more deep into this topic, and I think I pretty well grasped what it's all about. And I'm also trying to just help bring the message out there. But very importantly, I don't want to ride the hype train. I just want to try to make the topic understandable for developers like me. I don't want to talk like too high in the sky. I really want to make sure that people understand what it's all about, but they also know the limitations. This is something we are still actively investigating. Some companies are using it to some degree, but it's not really. We can't really solve any extremely large problems that we want to solve with quantum. We're not yet there. So I really want people to understand that this is very new, very exciting, but we need to keep realistic about the future of quantum.
Awesome. And I really love the story there. You know, you've gone from being a participant in the technical community through to I guess, looking at one of your heroes almost in the community and taking on that topic and going, that sounds really interesting, going to give it a go, and then going on your own journey then to actually giving back to the community. Because one of the things you haven't mentioned yet as well is you've been busy on the side doing a bit of writing as well.
Yeah, indeed. So actually, when I was doing these conferences about and doing talks on quantum, but also .NET, so I'm trying to mix and match those. I got a call from Apress, the publisher, and they asked me, we don't have any authors doing a book on specifically Microsoft-related quantum technologies. Do you want to write a book? And yeah, whenever I'm asked a question like that, I'm like, this sounds very exciting. So let's just do it. So indeed, yeah, I spent most of the lockdown time of COVID. I spent writing this book, introducing Microsoft quantum computing for developers. Again, trying to explain everything quantum for a software developer, and then instead of doing all theory, we just dive into the tools that Microsoft has provided throughout these past few years, doing Microsoft Q#, giving you loads of examples where you can write some code, do some debugging to trying to understand how this quantum world works, and just showing you also a little bit of Azure Quantum and what the future of quantum can be like. And to put the cherry on the top, this book has been reviewed by Bart de Smet, my hero.
Excellent. There we go. So it comes full circle.
Yeah,
Awesome. Love
exactly.
it. Love it. Good. So I guess we've got the context. And I always love, by the way, hearing these stories about people getting involved in the technical community, first by attending, let's say, but then stepping up and finding their own place in it. I love seeing that. So again, love that story. But I guess we're here to talk about quantum and Q#. I'm out of my depth. As I said before we went live, I can't promise I'm going to ask any good questions this evening, but I'll try. We'll see. I'll definitely learn something. So I think what I'll do, I'll bring up the slides here for you as well. And I think we're just going to have a bit of a discussion as we go through, aren't we? I may have lost your audio.
So, am I back?
You are back, yes.
Okay, so
don't worry, it's the whole pandemic thing. You're on mute. We've all been there at some point.
Yeah. No, so I was just saying, okay, I'm just going to go through these slides, and I'm going to tell you what my experience in learning quantum was like, what I think is important for you to know when you also want to work with quantum. And if you have any question throughout, just ask me. We can have a discussion about these things.
Sounds good.
So the first slide is about me, so let's skip that because we already had that. So the idea for quantum computing, of course, is to help us solve problems that we cannot solve at the moment. What kind of problems these are problems that are quite exponential in nature. And when we introduce lots of data, we can't actually find a solution in like a small amount of time. Typical examples of this are people mostly use the example of encryption and cryptography, where we actually designed algorithms ourselves that can easily calculate something to encrypt data, but are very hard to break in the other way around. So we cannot decrypt data by just brute forcing, because our current classical computing systems would take hundreds, even thousands of years to find a solution to those problems. But of course, this is something we did ourselves. We don't want our encryption to be broken, so that's a good thing. But of course, there's also other kinds of problems that we would like to solve, that are actually not possible to solve at this moment because they are so complex. A very good example is pharmaceutical companies doing drug development. When you introduce a drug to your system, the human body is so immensely complex. There's so much things going around inside of your body that we cannot create a computer model that fully simulates what is going on, because it's just too many variables. There's too much data. There's too much interactions. So it's just not possible. And that's the reason why we unfortunately still do animal testing, because when a pharmaceutical company creates a drug, they can't create computer models to exactly know what's going to happen, so they need to do all kinds of testing and just do a little bit of trial and error, basically. So our ultimate dream, is that quantum computers, which are a different kind of computers, I'm always going to talk about classical computers. That's what we are using today, laptops and PCs and cloud environments. And then quantum computing is going to be this new type of computers, and hopefully they will help us solve these problems, or at least part of these problems. And actually, the example that you can see in my slides right here is one of the first times I got introduced to how complex even a simple problem can be. I was doing high school, and I was in a class, and I was already finished with my exercises, and the teacher knew that I was doing some programming in my free time, because I wanted to be creative as a teenager, and I was doing this using programming languages. So he came up to me and he said, "I have a challenge for you. If you know a chessboard, and if you know something about chess, you know that the knight's piece, which is represented by the horse, can take a very specific jump. It can jump from its original position on the left-hand image to 8 different kinds of positions all around. So it's like 2 positions up and then 1 position left or right, or the other way around, which is called a horse jump." And he asked me, "Can you start on a random location on this chessboard and then jump around the chessboard and visit each square exactly once and fill out the entire chessboard?" And I was like, this is a very fun thing to program, because you can create a recursive algorithm that just brute forces this and just tries to jump around, and when it's stuck, when it can't go any further, it can backtrack, so it can step back and it can try different routes until it reaches its final destination. But then, yeah, I did the programming. I think I was about 15 or 16 years old, and I ran the application, but it didn't really come to a finish. So I thought I made a mistake. I tried again, let it run overnight. And I was a teenager back in the 90s, so I just played outside and I forgot about the problem. I abandoned it, basically. It was only later, when I was already working in software development, that I got to know that this problem is actually a very popular problem. It's called the Knight's Tour. And when you make the wrong decisions by accident all the time, this can run a very long time. And this is why I'm using this example. If you look at this, it's just 64 squares. How hard can it be? But there's so many different permutations that your algorithm can actually work for hours or days or even years to solve this problem. Of course, CPUs today are a little bit faster than they were in the 90s. And of course, when you take another approach, like when you already know a little bit more information beforehand, this can be easily solved. But it's just a very simple example. So hopefully you understand what the complexity of an algorithm can actually be. And this is also how I introduced the problem solving in quantum computing in my book, by using these simple examples and the exponentiality, the exponential nature of some of our problems.
Gotcha.
Yeah, and
Is that related to kind of the PNP kind of idea as well, then, in terms of whether it's solvable or not? Yeah, gotcha.
Yeah, indeed. Yeah, exactly. So when you look at time complexities for algorithms and stuff like that, that's exactly what all this is about. And then why would a quantum computer be a kind of computer that can help us solve these problems? Well, basically, the quantum physics, which is a very specific thing in physics, which talks about how very tiny particles interact with each other. For some reason, it behaves very differently from our macroscopical world. If you look at microscopical particles, and this is already something that was investigated and actually worked on in the beginning of the previous century, so the beginning of 1900, scientists were looking at these phenomena. They were doing experiments, and they saw that on a very tiny level, things were behaving very, very weird, and we don't really understand why it's doing things like that. But we know it does work, and we know that things work like that. So in this slide, you can see that there's something called superposition and something else called entanglement. Well, superposition is basically a property of some kind of, or a state of a property on a very tiny particle that can be in multiple states at the same time. It's something very weird. In the image, which is just a graphical representation, it's not how it really looks, there's the spin of an electron. So we all learned in high school that an electron has a certain spin, and this spin is basically a binary property which can be up or down. But when that object is in a state of superposition, it is said to be spin up and spin down at the same time, which doesn't really make any sense in our language, but it is something that is actually happening in the real world. On a macroscopical level, this doesn't really work. Things have a certain property or a certain color or a certain smell, and it's only going to be that state. It's never going to be multiple states at the same time. And also something even more weird is that when that superposition state comes into contact with our reality, when you measure it, for example, so when we have very good optics or very good microscopes, and we measure like some of these properties, the moment they are measured, they decide to take one of these distinct states, one of these binary states, instead of being in superposition. So somehow it's like the value of that property or the state of that property did not yet make a decision until we measure it, and then it will flip or it will collapse into one of those states. The only thing in our real world that I can think of is like a USB key, like the classical USB thing. When you try to plug it in, it will never work. You can turn it around like 5 times, it never works. But only when you look at the USB slot, then it will fit. So this is basically what's going on a microscopical level all the time. Everything that's inside of your body, all the molecules, all the electrons and the things that they are made of, they jump into superposition and out of superposition all the time. And that's also the reason why it only works on a microscopical level. When you look at a macroscopical level, we exist out of billions of these particles. And for example, when a human being in its entirety would be in a superposition of being on this chair and in my living room at the same time, the chance of that happening is so very low, because then all of the particles inside of your body need to be in that same superposition at the same time. And just probabilistically, that's never going to happen. There is a very, very, very small chance that it can happen, but it's never going to happen because the chance is too small. And that's what this superposition is all about. And it's phenomena like these in quantum physics that we are trying to leverage in computing to help us create a different kind of algorithm. And hopefully, when doing this in the correct way, we can hopefully solve these kinds of issues. The thing on the right-hand side is what we call entanglement, which is another very weird phenomena in quantum physics, is where when we have two particles, in some occasions they can be entangled, which means that they can influence each other in some way. Again, we don't really know how it works, we only know that it works, and we can do experiments to prove that it works. But basically, when you have one particle in a superposition and you have an entangled particle also in superposition, when you measure only one and it collapses to a specific state, the other particle will immediately collapse to the opposite state at the exact same time.
Right.
Which is very weird. They even did experiments on very large distances where particles were entangled and then split up very apart of each other. Large, vast distances, different laboratories in different countries. And then they did experiments where they measure one and then the other one always collapses to the opposite state. Again, immediately, there's no time difference. So there's no communication whatsoever because nothing can go faster than light. And then there's wild theories about this, like wormholes and stuff like that. But that's all nonsense, probably. We just are not smart enough to comprehend how this actually works.
Gotcha. This is all really fascinating because, and I love the analogy, by the way, around the USB. Like, I think anyone can understand that because we've all been there. You try about, like you say, 5 times and it still doesn't work. You look at it and then suddenly it works. So I love that analogy. I'll definitely use that in the future. But it's really interesting because I studied computer science back in university. So the whole concept of the 1 and 0, which I think you flashed up on screen a moment ago there, it really kind of resonates because that's how we're really used to thinking about computers right now. Is it's either on or it's off. The bit is on, the bit is off, and it's simple as that. But I think that's fundamentally just to kind of encapsulate back to what you were saying at the beginning. You know, we've talked a little bit about the theory there, but this is why it's so important, because what if you didn't have to be 1 or 0, but you could be both, and then you can kind of collapse those all down? That's where it's so powerful, isn't it? Because it suddenly enables this huge amount of processing power.
Exactly, indeed. And now that you're mentioning that, I'm just going to show you the slide where I try to explain the reason why it's so powerful. You were talking about, indeed, we have the binary states 0 and 1. So for quantum computing, we actually have a third kind of state, which is called the superposition state, where it can be 1 and 0 at the same time. And this is the thing that gives us that power. But why does it give us that power? Well, basically we can, and this is a little bit of mathematics, and I'm very sorry for that, but don't be afraid. I was afraid of mathematics when I started with quantum computing. I bought some books that were only mathematics, and it hurt my brain. But actually the math that is being used can be it can just be high school math. It's just a little bit of linear algebra. In this case, what you basically see is a linear combination from linear algebra, where you have a linear combination of these 0 and 1 state, where it can be something in between. And we can write that down as a mathematical formula that says we have some kind of alpha times the 0 state, and we have some kind of beta times the 1 state. And this actually gives us the opportunity to describe that superposition state. And when you have a perfect superposition, where you have like a 50-50 percentage, which is very handy for a randomizer function, when you just put a very tiny particle in some kind of superposition and you measure it, it will probably have a 50-50% of collapsing to one state or the other, which is a cool randomizer. If you draw that down mathematically, this is what that looks like. Alpha would be 1 over square root of 2, and beta would be 1 over square root of 2. The reason it's written like this is because alpha and beta are the percentages of the chance of collapsing to that state, but it's not the percentage, it's actually square root of the percentage. So basically that alpha and beta value, you need to take the absolute value and square it, and then both of them need to equal 1, which means 100%. So in 100% of the time, it will collapse to either 0 or either 1. But now you can work with these values. You can change the superposition state to have a higher probability of collapsing to 1 and a lower probability of collapsing to 0, for example. And this can all be done mathematically. You can just write that down and do the calculations like that. Of course, mathematicians always like to make things more complex, pun intended. So alpha and beta are actually complex numbers, but we don't really need to get into that.
Very good.
So you can just think for a perfect superposition, 50-50, it's 1 over square root of 2, because you need to square it, and then you have half plus half equals 1, which is 50-50. But now that power comes, because when you have alpha and beta and you think of only one bit, of course you have these two values, so there can be one or the other. But when you expand your system and you have 2 qubits or 2 quantum bits, you basically have 4 probabilities, because now you can be 0, 0, 0, 1, 1, 0, 1, 1. So you have a superposition, you have a combined superposition state of 2 qubits, which can actually represent 4 distinct states. Again, and this is where that power of quantum computers come from. In order to represent all the different kinds of states in your problem, and if it's too many and you can't represent that with only your qubits that you have, in order to double the amount of states that you want to represent, you only need to add one single qubit. Because if we go from a 2-qubit system to a 3-qubit system, now we have 8 distinct states that we can represent in some kind of superposition. And again, adding one more qubit, 4-qubit system, has 16 of these probabilities. And this is exactly where that exponential power of quantum computers comes from. Again, when you look at a classical computer and you have a CPU, which today already has billions of transistors inside of it, so it can represent billions of tiny bits into some circuit, some electronic circuit. When you want to double the power of that CPU, you basically need to double the amount of transistors you're using. Right. But for a quantum computer, when you have a 100 qubit system, which is extremely powerful already, you just add one single qubit and you double the processing power, which is cool. Of course, I'm not talking about the actual physical implementation. That's what we are struggling with today, because which is expected, only adding one qubit to an already existing system actually makes that system a lot more volatile and a lot more unstable. which of course makes it more difficult to only add that single qubit. So we need to try to solve these kinds of problems. So of course, nature always has some kind of problem for us that we need to solve, of course. But yeah, this is indeed where that power of quantum computers come from.
Gotcha. So if I then try and kind of simplify it a little bit there in my own terms, if we were trying to solve that formula like we got on screen there, if we just had the two variables, for example, it might take us a certain amount of time to figure out that formula. But because we've got more variables that we can play with in parallel altogether, it cuts effectively the amount of processing time to work out that formula. That's kind of the idea, I guess, in a simplified way.
Yeah, and well, actually, the way I understand is that not for all problems, but for some problems, you can actually encode all of the different solutions as these states. So when we have, for example, 16 different probabilities or 16 different states, we can have, for example, 16 different solutions to our problem. But now we want to find the correct solution to our problem. And with quantum computers, when you can encode all of these different probabilities, and in real life, when we have very difficult problems, we have billions of possibilities. So in order to represent these billions of possibilities, we only need not a lot of qubits, because again, just adding qubits to your system exponentially increases the amount of states you can represent.
Gotcha. Because
now
there's multiple states here, yeah.
Exactly. And now we can write algorithms, and some of these algorithms are based on what we call, and I probably forgot the name, the Fourier transform. You probably know it from audio processing also, but you also have the quantum Fourier transform, where you can basically change these probabilities, and you can increase the probabilities of some of your states and then lower the possibilities of other states, where you can basically change this, and then in the end you just do a measurement, because of course when you measure this system, and when in the bottom you can see this 4-qubit system that has a superposition of 16 states, but when you measure it, the result will only be one of those.
Yes.
But if you change those probabilities in your algorithm, and then at the end you do a measurement, the one with the highest probability will probably be your solution. Or at least it will be the solution that your quantum algorithm will provide you. And in many cases, checking if your solution is the correct problem is actually very easy on a classical computer. On a classical computer, you can work, because you already have a solution, you can check if it's the correct solution.
Yep.
And if it's not the correct solution, you just run your quantum algorithm again. Of course, quantum algorithms, they are in many cases not deterministic, they are probabilistic. Again, we are working with probabilities. So when you have like a 76% chance of a specific state being your solution, you just check it in a classical way, and if it's not your solution, you try again. And like in the end, it's still going to be quicker than trying to do it all the way classical. And that's again really the power of this quantum computing.
Gotcha. No, it's really interesting, because I'm glad you mentioned about the probabilistic side of it, because in my mind I was thinking a lot of this sounds like almost modeling and figuring out the kind of ratio or the potential of certain scenarios, and it is, isn't it? It's just using that qubit concept to help us simplify I say simplify, that's probably the wrong word here, but come up with more combinations of things that we're working on in parallel, to reduce that processing power over time, then processing time, I suppose. Yeah,
exactly. And I can actually see that somebody's asking a question. So what is a qubit actually, or exactly? So yeah, indeed, this is all theory. So quantum computing has actually been theorized in the early 80s and in the 90s, which is already 30-40 years ago. But we didn't have the physical capabilities of actually making it work. So in theory, many algorithms already exist. Again, I talked to you about cryptography before. The current cryptography that we're using for example, private public key encryption is already broken in theory. We have the algorithm to break it. We just don't have the physical hardware that is capable of actually implementing that algorithm. So there is a difference between the theory and the actual practice. So in practice, we are trying to leverage actual physical particles to represent our logical qubits. in quantum computers. So again, when you see in the bottom here a 4-qubit system which has 16 possible states, these are what we call 4 logical qubits. Different companies like Microsoft, like Google, like IBM, like universities all over the world, they are trying to create these quantum computers, but we still don't really know what the best quantum computer can look like. So every company is doing it in their own way. Some companies are using photons, so the elementary particle of light, because they have properties that also can be in a state of superposition. And they are trying to put those physical objects in a space where they don't get interaction with outside nature, with like waves from the sun, or with the temperature rising or going down, or even interacting with each other. So they are trying to create these kinds of quantum chips where these particles are isolated, and we can actually leverage their superposition properties. Other companies are using electrons, and actually some others are using ions. And again, I think that electrons, they are manipulated using microbeams, microwaves, to actually try to very carefully change these superposition states. I know that other systems work with ions, and they are being manipulated by laser beams. So again, every company is trying to find the ultimate quantum computer, to hopefully make it stable enough so that it can work with a large number of qubits. I was already talking about logical qubits before. Basically, the logical qubit is the thing that we are going to use in our algorithms, but the physical particle that is going to represent that qubit is what we call the physical qubit. And of course, we are just talking randomness here. We're talking probabilities. So we want to do some error correction, or at least when we encode our algorithm into these real physical particles, we want to do it multiple times over so that we can take an average, so that the result will be better for us, that we have a better result. And this is what we call quantum error correction. So one logical qubit can actually be backed by hundreds of physical qubits. So when some companies are talking about, we have a quantum computer that has 1,000 qubits, we don't really know, are those 1,000 logical qubits or 1,000 physical qubits? So this is, of course, marketing talk. So yeah, it's very difficult to create a lot of physical qubits in the same space that don't interact with each other, or at least interact with each other when we want them to interact with each other, and don't have them interact with each other when we don't want them to interact with each other. So yeah, again, this is something that is outside of my knowledge area. I'm not into how it's physically done. That is up to university people and people doing PhDs on that stuff. I'm really looking into this from a theoretical perspective, and also using the tools from Microsoft where we can already play around with these and hopefully learn for our, maybe in the future, actually doing quantum programming.
Gotcha. No, awesome. And there's a lot of love in the chat, by the way, for the topic and for just what we're talking about here. And I think actually I'll just bring up this question from a good friend of the channel, Peter, who I think raises an interesting question, which maybe takes us a bit towards some of the Q sharp side of things as well,
Yep.
on the implementation side. Can you speak to qubits from an object-oriented dev, and what about the principles of quantum computing? I hear operationalism being thrown around. So let me bring your screen back up here.
Yeah, indeed. So basically, quantum computing today, or at least quantum programming today, is a bit of a combination between programming circuits and then already a little bit of more high-level operations that we can do. So I don't know for the rest of the world, but here in Belgium, when I was in high school, we had a class where we had these physical boards that had different components, like an LED, a button, a buzzer, stuff like that. And then we had wires that we could connect from one to another. And there were these logical ports in between. So you could have like two buttons that go into an AND gate, and then the output of that AND gate could go into a buzzer. And then you could physically see what was happening and what these gates were doing. This is basically what a CPU is doing in your laptop all the time. And for quantum computers, this is actually what we are programming today. So let me just show you with a little example. So Microsoft has created a language, I didn't talk about this yet, Q#, where you can create just a new project. Of course, in this case, I'm going to create a console application, which doesn't really make sense for a quantum algorithm, but that console application is actually just a simulated environment where I can run quantum algorithms on my own laptop, so I don't have to run it on a physical quantum computer, which makes my life easier to show you things. So let's call this Q589 because I have no idea how I call my folders. There's already many of them. So create project.
And of course, you generated that number using some quantum algorithms there, right?
Yeah, you believe that. So yeah, in Q#, there is actually a language that looks a little bit like other .NET languages. It's a little bit like C# and F# combined, where you have namespaces, you have curly braces if you like them, you have namespaces that you can use or open. So in C# it's called using, in Q# it's called open. You have your entry point or your main method for your console application, and then you have your quantum operation. Of course, this is just sending a message to the console, so we're not going to do that. But now, the algorithm that you're creating is basically writing a circuit, just like having buzzers and buttons connected to logical gates, connected to outputs. We are going to do the same thing for quantum, because that is the state where we are in at the moment. So you can declare a qubit, and you can use the factory method qubit to generate a new qubit for you, and now you have a qubit which is just like a bit. So this is, if you create a variable in another language, a variable is of course made out of multiple bits together. Like an int variable is in most cases 32 bits. This is one qubit, only one qubit, so it can represent two binary states or the superposition state. Now, in order to change the state of this qubit, because by default, this will always be in the 0 state when you create or allocate a new qubit. If we want to change that state, we can put it through a gate. And in quantum computing, we have different kinds of gates, and those are also different from the logical gates. So in order to flip the 0 into a 1, we use the X gate. So I can just call a method called X, which puts that qubit through the X gate, and now it goes from zero state into the 1 state. And you can show that by using a message to the console. If you want to learn quantum, this is actually very handy programming language to do that, because you can use your .NET skills and do things like string interpolation to show you the measured result of that qubit.
And that's something really interesting, just to jump in there, Johnny. I think for me, as someone who hasn't really delved into this space, it sounds so complex. It sounds like something I wouldn't understand. I've got to learn a whole new language to go and work with this quantum stuff. But actually, what you've typed there, I'm reading it going, okay, yeah, I understand that. It looks like Q#. You're running some functions on what your input is there. You've got your type, which is a qubit there, and the explanation makes complete sense. So, everything that you're saying is actually, back to your point in the very beginning, is very relatable and understandable. So
exactly.
That's what I'm saying.
And that's what I like about these things. So Microsoft is working on their own quantum computing computer. Quantum computers are still in the very early stages, but we already have the tools, so we can already learn to use them. Because these tools are actually based on the concept of universal quantum computers, which is something that most companies are working on. So this is actually where we want to be in the next, decades. So we already know that this language will be there for some time and it will work like this. So yeah, I just ran the application by doing .NET run. Again, this is a simulated .NET application that actually runs a Q# interpreter, and that will actually run all the mathematics in memory. And that's also why you can't allocate lots of qubits here, but you can learn it. You can learn from it. So the result equals 1, because of course I said it starts in the 0 state, we flip it around to the 1 state, and so on. Now, if you want to put it in superposition, there's another gate called the Hadamard gate, or the H gate. So just again, put your qubit through that gate, and save your file, compile with .NET Run, and see the result. Now, the Hadamard gate puts a qubit into superposition, or if it's already in superposition, takes it out of superposition. But now we have basically a randomizer. We created a randomizer because when I run this application multiple times, it's going to be 0 or 1, about 50-50. In a simulated environment, we are using the pseudo-random generator that we already know from other programming languages. But when you run this on a physical quantum computer, for example, on Azure Quantum, it actually be run on physical quantum hardware, and it will be really random from our nature, basically. Now, when I was talking before that quantum programming language is actually a combination of creating circuits with these elementary gates. The cool thing about the language of Q# is that you can create operations, and an operation is actually something that does quantum operations. It is also very tied into the linear algebra that you need to perform these operations, because basically, as I told you before, a qubit is a linear combination. We can express that as a matrix from linear algebra. And then when we do operations on that, we basically do matrix multiplications with operation matrices. And this is what is happening in memory when you're doing a simulated thing. But when you run that on physical hardware, it actually works like nature would do it. But what I was saying is that this looks very low level, but of course we can just add operations as many as we want, and we can rename something. We can do something like put in superposition, where we have a qubit as an argument. Then of course just do the age of our qubit. And now we created an operation that we can use. We can put it in some kind of NuGet package even if we want. Now it reads like put in superposition. So you can create your own higher level programming language by just creating these operations that maybe do multiple of these quantum operations one after the other. And now we can create higher level programming languages that basically put a lot of these logical things one after the other. And that's also basically what we are doing in C#.
Fascinating. It's interesting, and even the comment like you could make your own NuGet package out of that just made me laugh, because again, you know, we're talking about things which are really pushing the boundary of what is possible from a computing perspective, but bringing it back to those concepts that we already know, package management and all these things. It's just fascinating. I'm just trying to apply some of the just think of how you could apply some of this into the real world. And I guess, would you see examples like maybe we have today? Maybe this is a bit of a poor example, but bear with me here, but like a microservice almost type example where, you know, you've got your quantum microservice that is going and, I don't know, breaking whatever code is trying to break, and then going to go back and push it back to whichever microservice. How do you kind of see it, I guess, interacting and kind of being used at the moment?
Well, that's probably exactly how we are going to use it. So when we are creating programs, creating algorithms to solve our problems, we are actually always going to have a combination of classical hardware, classical algorithms, and quantum hardware and quantum algorithms. And that's also where Azure Quantum comes in. Azure Quantum gives us the physical quantum hardware. We can create a piece of Q# that does some processing and it has some kind of result, and basically you push that into a service on Azure Quantum, which is one of your microservices. It does your processing, and then from your classical microservice you push the inputs, then the quantum part does its thing, you get the outputs from that, and you can go again in your classical algorithm. You can work with those values there. So it's always going to be a combination. So we're not really going to put any classical algorithms on quantum hardware because that would be too expensive to run. We're just going to use it for what it's capable of doing, which is helping us in that quantum world. So it's going to be indeed that combination. So Of course, all of this is still in its early beginnings. Microsoft is also still working very heavily on how all of this should work. But maybe this is a good segue into Azure Quantum, if you allow me to.
Yeah, absolutely. And just while you're switching over, just to pull out something that you said in there as well around, I guess, the cost and the complexity, bringing it back to the channel, cloud with Chris, thinking about the cloud aspect. This is one of the things we hear commonly with that on-premises to cloud migration is you can scale as you need, you pay for what you need, use what you need. But in this scenario, how powerful is that? You don't need to go and buy your own quantum computer. Instead, it's just there's a cloud provider where you can go and rent for what you need and solve the problems you need and pay for what you use. So it really is bringing that cloud model.
Exactly.
Fascinating.
It's just that, indeed. Of course, we need to be careful when we say we're never going to run a quantum computer in our living room, because that's what they said about classical computers a long way back. But indeed, it's so expensive to keep a quantum computer stable. It runs in high-tech laboratories. So in this way, we can just have that power at our fingertips. So indeed, this is something that I've never seen before. Quick create and advanced create. Let's select advanced create. It's just a resource in Azure, like we all know it. You pick your resource groups, your workspace, some comprehensive name, and not what I've typed right here. I'm just going to keep it on East US because I think that's the only place where they have quantum computers running. You need a storage account to store your input and output data if you run quantum algorithms. And this is actually what you were saying, Chris. So Microsoft allows us to pick out of a list of their hardware vendors. So they have multiple hardware vendors where they are working together with. They have Honeywell and IonQ. And indeed here, if you, for example, say I'm going to use IonQ, I'm going to look at their pricing, you can see that they charge us on the right-hand side, they charge us for every 1 quantum gate shot or 2 qubit gate shot or 1 qubit gate shot, which when I put a qubit through an X or an H gate, that's a 1 Q gate shot. So I put 1 qubit through 1 gate. So I'm going to pay this amount of money for that. So if your algorithm puts hundreds of qubits through hundreds of gates, you can basically calculate what that will cost you when you run your algorithm.
So it's almost like a serverless pricing model then,
exactly.
pay per number of transactions. Gotcha.
Yes. Yeah, indeed. And then you create your Azure Quantum Workspace, and that gives you access to that physical quantum hardware. And actually, I'm just going to show you the rest. I'm not going to create it because I already have one running. It doesn't really give you a lot of information in the Azure portal. You can just see your job management, which means which jobs, which algorithms have you pushed to your quantum workspace, and have they already finished processing, yes or no? That's it. But from something like this, and maybe let me show you something that I've prepared beforehand.
Excellent desktop background. I appreciate that.
I can't even remember what it was.
Here's the Sea of Thieves logo.
Yeah, Sea of Thieves is my alcohol.
Or rum, you might say.
Yeah, my rum.
There you go.
That's a good one. So this is a very simple superposition algorithm or entanglement algorithm where I allocate 2 qubits, and instead of putting them through the Hadamard gate, which puts them in an equal 25, 25, 25, 25% probability of its 4 possible states, I'm just going to use some mathematics to put it in a different kind of superposition. Basically, RY, I didn't talk about this, but don't break your head about it. I'm just going to rotate that linear algebra vector in that vector space for quantum physics stuff. I'm going to rotate that vector for 2 pi over 3 radians. So it's basically just rotating a vector in a 3-dimensional sphere.
And that explanation, by the way, folks, definitely stands up in like a maths degree. So if you're studying, just put that in your exam, you're good.
And What this does is, instead of making a 50-50 or a 25-25-25-25, because we're talking 2 qubits, no, we're talking 1 qubit. We only apply this to the 1 qubit. So we have, instead of doing the 50-50, we actually do 25-75%.
Gotcha.
So we are changing those probabilities by rotating that vector this amount of radians. And now, by using a CNOT gate, which is a gate that takes 2 qubits, which is basically kind of an if gate, that gate says, if the first qubit equals 1, then I'm going to flip the second qubit from 1 to 0 or 0 to 1. But the first qubit is in the superposition state, so it's not 0, it's not 1. And we basically entangle that second qubit to that first qubit. And now, with this project, I can actually push that to Azure Quantum and make Azure Quantum evaluate that thing. So you just use the Azure CLI to do that. And actually, when you have logged into your Azure subscription using Azure CLI, and you set your quantum workspace as the default workspace you want to use, you can ask for a list of all the quantum targets. And you can see that I'm not going to talk about the Microsoft Quantum Inspired Optimization right now, but these bottom 2 ones are actually quantum QPUs, or quantum processing units. The first one is a real quantum processing unit, and it has an average queue time of 133 seconds. And then there's a simulator. The simulator is free for you to use, and then the QPU, this is the one you pay for. This is the actual physical quantum hardware. So just as an example, I'm just going to use the simulator. Otherwise, we're going to wait a couple of minutes, which I don't want to. But you can, in your folder where your application exists, you can do Azure Quantum Execute on the simulator or the actual QPU. And I want to see the result as a table. So if I run this, it will push that Q# code to my workspace. And what actually happens is the same thing as happens in .NET. Microsoft has created an intermediate language, which they call QUIR, or Quantum Intermediate Representation. They compile your Q# down to the Quantum Intermediate Representation, and they can push that code to the physical quantum hardware. And then each hardware vendor, they need to interpret that quantum intermediate representation, and they need to translate that into their machine statements for their actual quantum computer. And then their quantum computer will put its physical qubits through all of these operations, and it will give you a result. And the result you can see right here. We now have indeed our result for our quantum algorithm will be 2 different possibilities. It will be 0 for the first qubit and 0 for the second qubit in 25% of the time. And it will be 1 for the first qubit and 1 for the second qubit in 75% of the time. I talked about the fact that this is entangled qubits. So they will always be 0 or 1, both of them, because they are entangled. I talked in quantum physics, it's the opposite. In quantum physics, when you measure one particle, the other one will automatically collapse to the opposite state. But for quantum computing, they decided in this case that they will be equal then.
Same. Yeah.
But it's just something that we basically decided for this specific thing. But yeah, what Azure Quantum did is actually run our algorithm not once, but in theory an infinite amount of times to actually get these probabilities. Of course, it doesn't run it an infinite amount of times. It runs it, I think, by default 100 or 1,000 times to get these numbers. Gotcha. So when you run it on a physical quantum computer, it will be a little bit more random, because we don't run it an infinite amount of times. It will be like 1.26 or 1.25, 111 or 1.24999, something like that. But this runs on a simulated environment. So basically what happens on a simulated environment, it just does all the linear algebra. And when you do the mathematics and the linear algebra, you have beforehand, you only need to run it once. You know what the probabilities will be because you calculate it.
Gotcha. No, really interesting. And I think there was something earlier that you said as well around like that intermediary piece, and then it going down to the quantum computer code. Again, all concepts that we're familiar with, right?
Yeah,
You've got your think of .NET, and you've got your intermediary layers. You compile down to your assembly or whichever, however you're speaking with your underlying processor. these are all kind of concepts that we're familiar with, and it's almost reinventing it for that different platform, isn't it? And using these different principles. Really interesting.
We just use the same principles we already use because we know that they are quite successful, and we just most major companies are doing it like this, and I think Microsoft already has become very popular with their core or quantum intermediate representation, and other companies are also wanting to use them, so that also different languages, not only Q#, but also languages from other vendors can be compiled down into that same quantum intermediate representation, so that we can all leverage the same hardware. We don't need to rewrite all of those compilers, but we can choose as a developer which programming language we are the most comfortable with, which I really like.
Gotcha. We've had a few more questions in the chat, by the way. So Chiranjib Das asks, I'm really curious to know where we can use this to solve any real-world problems. And I guess that's maybe part of the challenge at the minute, is where this is so early, isn't it? A lot of this is more theoretical rather than applying it to specific scenarios.
Yeah, indeed. So for the examples that I already talked about, like drug development and cryptography, it's too early. We don't have the physical power to actually do that, but we can already use it for example, quantum machine learning is very hot at the moment, where we create a part of our, or where we encode a part of our problem into a quantum solution, which can already help us for a tiny particle of that. And again, we can learn from that. And as I told you before, the Microsoft Quantum language Q# already has this higher level libraries, where you do, in the top, you can do open microsoft.quantum.something, where it's in the documentation. You can see that there's already libraries for specific use cases, where there's already higher level functions that we can use to solve these kinds of problems. I talked about the quantum Fourier transform before. We don't need to put these qubits through all of these gates. The quantum Fourier transform itself is already there as an operation we can use in a namespace we can open from the Microsoft Quantum Development Kit. Exactly. So I can see that you're indeed looking at the documentation from Microsoft, and there's so much information there. If you are really interested in this stuff, just look at that documentation. It's great. There's even interactive examples of Q# code where you can just change the Q# code online to see what is happening, and you can learn from that. There's step-by-step processes how to recreate already existing algorithms for you to learn how everything works.
It's awesome. And I think this is probably the main point, isn't it? Is that we really have just scratched the surface. As fascinating and as interesting as this has been already, looking at all of this, this is only just really scraping at the very beginnings of this. I'm certainly intrigued to go and learn more about this, and I'm glad, but I'm also worried because, like you said before, in terms of having those side pieces where you kind of go down and get distracted and then start looking and building projects around it, I fear for my time, but there we go. But we've got another question, actually, just before we start wrapping up here, just again from Peter Piper here. So, do we have to think of map and reduce to think of optimization? And based upon the interface interop between, do we need to think of async and existing patterns, claim check, for example? So I guess what Peter's asking there is effectively the types of patterns that we'd see in some of those implementations and some of those patterns that we may see in our current forms of programming, perhaps.
Yeah, I think it's going to be a little bit different indeed. The code that I've seen in Q# and many of these algorithms are in most cases quite mathematical in nature, indeed. So also the question from before about object-oriented programming, I don't really think it's going to be relatable to something like that. So yeah, it will take some adjustments from us as a developer to really understand what is going on, because it's an entirely different kind of algorithm.
But in fairness, again, think of computing back in the day, right, when you had the Enigma machines, etc., and thinking about the types of computing that was happening there. I think we're just at the start of something like that again, aren't we? And all of that research and investment has to build up until you can get to a state where we have computers like we do today, but in a quantum sense. Then
indeed. And again, there will probably be there will be higher level entry points for this, where we just like in today in Azure, where when you want to do machine learning in Azure, you already have some tools that you can leverage and use to build your models and to work from that. I think we're going to create the same things in quantum. We're going to have these little building blocks depending on what kind of problem you want to solve, like optimization problems or encoding problems or stuff like that. You just pick the stuff that's already out there. That's why I talked about the NuGet packages before. You just use the things that are already there, combine them, and then solve your problem that way. Think of it as a very advanced low code approach to solving your problems.
Awesome. No, this has been really, really fascinating, Johnny. So thank you so much for coming onto the show and talking about this. I'm sure there are a few folks who have been in the chat who will be, I'm sure, starting to look at the docs, and no doubt will be in touch, I'm sure. But thank you so much. It's been a really, really interesting topic, and I definitely know a lot more than what I started.
I really love talking about this, and I can talk for 3-4 hours if I want to, but of course people also want to enjoy their night.
Absolutely. But no, we'll have to get you on again to maybe talk about a deeper level, or maybe certain areas or certain topics. So I think there's an open invite to come back, because I've really enjoyed it.
I'll remember it.
Excellent. But Johnny, thank you, and we'll see you again soon.
Okay, thanks for having me.
So, folks, there we go. A really, really great session around Q sharp, around quantum in general, and just understanding some of those foundations and some of those concepts. If you've liked the episode, if you like the show, please do share it on, because the more people who know and can tune in, obviously get more guests on. We can bring Johnny back as well to go and talk about this again. So please do share on. Next time, I think the next episode that you'll see coming out is going to be 2 weeks again from today, and this time it's going to be all about things to consider before migrating old .NET applications to cloud. So sticking with that developer theme, not quantum this time, talking more classical computing, but of course some of those things you might want to consider before you migrate your .NET applications to cloud. So that's it for this evening, folks. I hope you've enjoyed. As normal, please stay safe, please stay healthy, look after yourselves, and as always, thank you for watching. Until the next one, bye for now.